Welcome back to the new playlist of Data Engineering Mastery. This is a new playlist where the oldest one was about mathematics of thinking, where we discussed about algorithms and maths. Within this new playlist, we'll be talking about real production pipelines, real problems, real fixes, real failures. And by the way, I am launching a Python formation. If you wanna subscribe, you can fill in the form within the description. And without further ado, let's get started. Today is about PySpark, but not the basics, not how to create a Spark session, not how to read a CSV, that is tutorial content. This episode is about the things that actually matter when you take a Spark to production. So 5 patterns, all with code, all drawn from real production incidents. By the end of this video, you will have a checklist of 6 questions to ask before any Spark job goes live. So let's get into it. So 3 stories from production that tutorials never prepare you for. Story 1, the join that hang for 4 hours. A data engineer joined like a 500 gigabyte fact tables with a 2 megabytes country lookup table. Standard join, no hints. Spark choose a source merge join. Spark shuffled like 500 gigabytes of data across the network to collocate matching keys. The job ran for 4 hours before timing out. The fix was 2 lines of code. We will see exactly what they are. Story 2, one executor did all the work. A group by on customer ID column where 18% of rows belong to one key, VIP Corp. Spark put 18% of the data into one partition. One executor was stuck for hours, while the other 99 executors finished their work within minutes and sat completely waiting for the other executor to finish. So this is a classic data skew. Classic fix is salting. The story number 3, the job ran fine. Then the UOM, a loop processed 10 gigabytes data frame 3 separate times. Nobody called the cache function. Every action recomputed the same data frame from scratch. 3 actions, 3 full scans, 13 gigabytes of computation. The job ran out of memory on iteration 3 and was killed after 2 hours. So every one of these is preventable. So let me show you how. First of all, so pattern 1 is about partitioning. The most misunderstood concept in Spark. So the wrong partition count is a multiplier on every problem. Too few partitions, most of your cluster sets EDLE. Too many partitions, small like file problem, scheduling overhead. Understanding the difference between repartition and coalesce is the foundation of everything else. So here in the left panel, repartition N, this performs a full shuffle across the network. Every row is hashed by its partition key and sent to a new partition. It's expensive, it's a network operation, and that's exactly what you need. Like you need it sometimes. Use repartition when you are increasing the partition count to match your cluster cores. You are rebalancing after reading skewed data. Like 4 partitions on a 100 core cluster means 96 executors are perfect. So you are preparing for a join on a specific key. Repartitioning both sides on the join key eliminates the downstream shuffle. Rule of thumb, target 2 to 3 partitions per executor core. 100 core cluster use 200 to 300 partitions. On the right panel, coalesce, and this merges adjacent partitions locally on the same executor. No full shuffle, no network transfer. It is cheap and it only works in one direction, decreasing. So use coalesce when after a heavy filter that drastically reduced your data volume. You had like 200 partition. After the filter, you have like 200 mostly empty partitions. Qualys 10 merges them cheaply into 10 balanced partitions before you write to disk. And critical mistake to avoid: never call Qualys to increase partitions. Qualys 500 on a 200 partition data frames give you 200 partitions. If you need more, use repartition. Pattern 2, which is the single most impactful optimization in PySpark. One function called potentially like 13 times faster. So look at the two diagrams at the top. Source merge join, the default Spark needs to like collocate matching keys from both sides, so it shuffles the large table all 500 gigabytes across the network. Every executor sends its partitions data to the partition responsible for that key. Runtime is 4 hours. Broadcast join, the optimized path, so the small table 2 megabytes is sent to every executor once. The large table never moves. Every executor has the full lookup table in memory and performs the join locally. For the runtime here we have is 8 minutes. Same cluster, same data. And the code is in the bottom panel. Two changes from the default. First of all, operationally increase the auto broadcast threshold from the default 10 megabytes to 50 megabytes of data. Second, explicitly wrap the small table with broadcast. The result fast equals fact dot join broadcast lookup comma country ID. So, and that's it. That's the entire change that you will have to do in this case. So after the join, always verify using explain with mode formatted. So look for like broadcast has hash join in the physical plan. If you see source merge join, the broadcast was not applied and you need to investigate. Any table under 200 megabytes, wrap it in a broadcast, no exception. Pattern 3, data skew. This is the hardest performance problem in Spark because it's invisible until you took at the you give it a look to the Spark UI. So look at the bar charts at the top. Partition 0 holds 18% of data. The remaining partition have like 5, 4, 3% and so on down to almost nothing. When you run a group by or a join on this column, the executor 0 process 18% of the data. The other 99 executors finish their tiny partitions in 3 minutes and then sit while waiting for the executor 0 to finish, as we discussed within the story number 3. So how do you diagnose it? How to do your diagnostics? So you're gonna open the Spark UI at the HTTP driver 1414. You're gonna go to stages. If you see one task running for like 13 minutes while the other tasks completed in like 3 minutes, I'm sorry, that is a skew problem. So one partition is too large. So the fix is salting. So what is salting? So if you look at the left panel, the skew join without salting, the whole key here is VIP Corp, has 18% of the orders. The join of customer ID routes all of those to one partition. Within the right panel, the salted join, we pick a salt factor, here 15. We add a random suffix to the ho key in the large table. VIP core 0, VIP core 1, VIP core 2, etc. up to VIP core 49. Now the 18% that was in one partition is spread across 15 partitions. We also replicate the small table 15 times with the matching suffix. So every salted version of VIP core has a matching lookup row to join against. Then wrap the replicated small table in broadcast to avoid a new shuffle. So the whole key is now distributed across 15 executors instead of one. So 18% of data is parallelized. Job completes in minutes instead of hours. So pattern 4, which is catching the most misused optimization in Spark. So look at the storage level table at the top. 4 options. memory only, which is fastest, but if data does not fit into RAM, Spark recomputes it. No eviction to disk, just recomputation. Use only when you are confident the data fits. Memory and disk, the default for cache. If RAM is full, spills to disk. Slower than memory only, but never causes recomputation, the safe default. Memory only, sir. It's like serialization. So it serializes the data before caching. So 2 to 5 times smaller footprint in RAM. It's slower to read back. Use when memory is tight and your data frame is large. Disk only, like for very large data frames where you cannot fit in RAM at all. Slowest but no eviction. Useful for checkpoints in mid-job. Now the code, like 4 rows to memorize. Role 1, only cache a data frame you will use more than once in the same job. If you use it once, caching wastes memory and adds overhead. Role 2, after caching persist, after calling persist, call an action to trigger materialization. So cache and persist are lazy transformations. Until you call like count or show, nothing is cached. This is the most common caching mistake. People call persist and assume it run, which is not. Rule number 3, always unpersist when you are done. On long running jobs, accumulated caches will eventually cause the OOM. Free the memory explicitly. And rule 4, cache is not persist. Memory only. Cache equals persist memory and disk. If your data frame is too large for memory, cache safely spills to disk. Memory only would cause recomputation, not what you want. So pattern number 5 that we'll be talking about, which is the window functions, the most underused feature in PySpark for data engineers actually. So if you are writing a self-join to a computer running total, stop if you are using a correlated subquery to get the previous row. Stop window functions do both in a single pass over the data with zero shuffle. Look at the code. 3 use cases. Running total per customer, we define a window spec, partition by customer ID, order by order date, frame from unbounded preceding to current row, then Spark some amount over window running, compute the cumulative sum per customer, no group by, no self join, one pass. Rank with group, partition by product, category order by revenue, descending rank over window rank, gives each row its rank within its category. So use dense rank if you do not want gaps after ties. So you can use row number if you always want a unique number regardless of ties. And lastly we have the lag and lead. So accessing the previous or next row, lag amount 0.0 gives the amount from the row immediately before within the same customer ID partition. Order by date, the third argument 00 is the default value for the first row where there is no previous row dot lead. So it goes in the other direction, so the next row. So if when you use lead, it's for the next row, while if you use lag, it gives you the previous row. So window functions are also the right tool for percentile rank within a group, running averages with a rolling window of n rows, first and last value within a partition, all without a single group by or shuffle. So before the checklist, let me make sure you understand the execution model, because this context explains why all 5 patterns matter. So Spark uses lazy evaluation. When you call filter, join with column, repartition, nothing run, Spark builds a DAG, a directed cyclic graph of transformations. No computation happens. So the computations only happen when you call an action, which is, for example, count, show, collect, write parquet. So when you call an action, Spark submits the entire DAG to the cluster, optimized it, with the catalyst optimizer and executes it. So look at the anti-pattern in the bottom panel. So 3 actions on the same data frame: count, distinct count, and aggregate collect. So 3 actions equals 3 separate jobs, each rescanning the source data from scratch. If the filter takes 10 minutes, that is 13 minutes in total. So the optimized version persists after the filter call count to materialize then use the cached data frame for all 3 actions. The filter run once, actions 2 and 3 read from the cache, now recomputing all the DAG over and over again. This is why caching is pattern 4 and not an after though. Understanding lazy evaluation tell you exactly when to cache, okay? So now the production Spark checklist. So 6 questions before every Spark job goes to production. 1. Is your repartition count appropriate? 2. Is a small table being joined without a broadcast hint? 3. Does your group by key have like high cardinality skew? 4. Are you using the same data frame more than once? 5. Are window functions replacing self-joins and correlated subqueries? 6. Have you checked the Spark UI for like stage bottlenecks? And post this checklist in your team's PR templates, add it to your code review process. It will catch the expensive problems before they read production. So like 4 takeaways for this video, the ones worth saving. 1. Partitioning repartition does a full shuffle, so use it when increasing or rebalancing. Coalesce merges locally with no shuffle, use it when decreasing. 2. Broadcast joins wrap the small side with broadcast table under 200 megabytes. Should never cause a sort merge join. 1 hint, 0 shuffle of the large table, verify with explain after every join. 3. Data skew detects with the Spark UI. Add a random key suffix to the hotkey. Replicate the small table n times, join on the salted key. 4. Caching persists before using a data frame more than once, call count to materialize always a persist. When done, cache equals persist memory and disk, not memory only. So drop a like if this saved you a 4-hour job, and tell me in the comments which one of these 5 patterns have you hit in production. The broadcast join one is the most common one I see in code reviews. Next episode, how to design a medallion architecture that actually scales using Databricks, bronze, silver, gold, but at the level where it does not collapse under real workloads. So see you in episode 5.